that be true of all the velocities you're likely to get to, or will you be doing some use possibly?
I'd like to be able to go to supersonic. Yes, yes. Yeah, the thing is, the easiest way for us to go supersonic is almost certainly to make it rotate very fast. And then in the moving reference frame, it's not clear that shocks or things like that will play a role. In that reference frame, they'll still be subsonic.
You can't make it go supersonic
in opposite.
one way and
I don't think so. But that, you know, doing shock experiments would be very interesting. We have to do it differently. Yeah. Okay. This is how we designed the experiment. We designed the experiment with this picture in mind. Okay? And this magnetic field, which I've shown you already. But this is what the flow almost certainly looks like in reality. And this is because the fluid Reynolds number for a magnetic Reynolds number of 100 is 10 to the 7. You know, it's an extraordinarily turbulent flow because the Reynolds numbers, the fluid Reynolds numbers are enormous. And this is just because liquid metals have this property. So you could ask, is turbulence going to help us or hurt us in this case? Is this a good thing or a bad thing? Now you might think that the turbulence is going to help us. I'm just going to get an enormous alpha effect. Those are kind of helical flows, and maybe they'll, on average, they'll contribute. But it's not so clear. We did simulations for the large-scale dynamo, which exists here, in the presence of the small-scale fluctuations. And what we found was that the critical magnetic Reynolds number varied a lot with the fluid Reynolds number. If it's very smooth and laminar, the critical magnetic Reynolds number is only 10 or 20 for this case. As we increased the fluid Reynolds number, and it became more turbulent, the critical magnetic Reynolds number went up further and further. Now this was found, Alex has studied this for small-scale dynamos also, where he looked at the production of small-scale magnetic field, found a very similar type of curve. But this is for a large-scale dynamo operating in the presence of turbulence. This thing has the interesting property that the critical magnetic Reynolds number got pretty big and then started to drop again. And we actually found there was a small-scale dynamo in the simulations here, large-scale dynamo here. This is what the flow has as a magnetic Reynolds number. And we can't go much above this because that's how big the experiment is. So we have this very pessimistic prediction now that in the presence of turbulence, this system will never self-excite. Okay? And I think you can understand this to some extent using the turbulent resistivity. So you can characterize the magnetic Reynolds number of the large-scale flow. This is the magnetic diffusivity, and this is the large V and the large L. You might also have a magnetic Reynolds number associated with the fluctuations, the small-scale stuff that we have. And in our experiments, these are related. If I drive the large-scale flow, it creates the small-scale flow, and that's about a third. About a third of this ends up as small-scale fluctuations in our experiment. What that means is the actual turbulent resistivity is proportional to the actual resistivity times a factor which increases with the turbulent magnetic Reynolds number. And so the critical magnetic Reynolds number that we have is enhanced by the fluctuations. In order for this system to self-excite, we have to go to much higher values than we initially thought to get it to work. And that makes it difficult. So we set out to measure the turbulent EMF. We took a probe and inserted it into the turbulent flow that measured the magnetic field, all three components, and the velocity field, all three components. And we were able, so here's an example of a waveform for the radial velocity field. It's turbulent, it's fluctuating all over the place. Here's the magnetic field, it's fluctuating all over the place. We're measuring that on a Hall probe. We can take those and beat them against each other, form the cross product, compute the EMF, and take its time average, and compute the alpha effect. Find the alpha effect that goes with the measured turbulent EMF. Okay? And From that, we know the strength of the turbulent EMF. And because we do this in 3 dimensions, we also know the direction of the turbulent EMF. I know if it points in the direction of the local magnetic field or in the direction of the current. Then what we did is we applied some seed fields. We did a test field case. We applied seed fields that created a measure, that induced a field inside the sodium. We were doing this from external coils. And then we measured the direction of the EMF. And the EMF opposed the current and not the magnetic field. Okay? So is this an alpha effect or a beta effect? It's the beta effect. Right, so in these experiments anyway, the turbulent EMF opposes the current. It tries to reduce any mean current which is developing. And this is nothing more than diffusion of the magnetic field by an eddy viscosity that's taking flux from one region and transporting it to another and mixing it. This is a classic mixing length formula which works very well for mixing milk in tea or anything else, and it works apparently just fine even for vector magnetic fields. Okay? And the scaling, in fact, this is the prediction from the original mean field theories. This is our measurement. And as we increase the velocity of our propellers and the turbulence levels went up, we measured the turbulence levels. This can be computed. And we found a very good agreement between those two. And so the lesson is, in turbulent systems, the magnetic diffusivity always has to be dealt with. Now, I think most people would accept that, but this is an experimental result that we actually observed in the lab. Okay?
Does it depend on whereabouts in the experiment you actually
We didn't measure it in as many places as I would like. Yeah. That's right. That's right. And we tried to get as far away from the wall as we could, and we tried to put it in a place where we had orthogonal currents and magnetic fields, because that allows us to distinguish between the two. So it's not so easy to build a probe which scans around, it turns out, in sodium. Good? Okay, so that's a lesson. For me, it was an enormous lesson. I started out with this picture of a laminar flow. I designed an experiment about it. I built the experiment to self-excite, and we didn't get a magnetic field. But I think I understand why. I think we didn't get a magnetic field because the beta effect was all-encompassing. And the reason it's important, the reason it developed so neatly in this experiment is the eddies that can develop are on the same size of the system. An enormous amount of free energy is available to the turbulence in this system. So there have been a whole collection of other experiments that have self-excited. Okay? There was an experiment done in Riga, or an experiment in Karlsruhe, and then most recently in Cadarache. Yes. We used a test field.
So what's the ratio of the, let's say, small b versus capital B? The b fluctuation b versus b naught?
Depends on where you are. There are certainly places where the induced field is 0. Max, factor of 3 bigger. Okay. So I'm not going to go into the details. Right. So these experiments have all created dynamos in the lab. So we can look at the first experiment. This is the Riga experiment. And it was in a cylinder. In fact, it was inside 3 cylinders. There's a cylinder down the center. The flow comes down the middle. It has helicity. It comes back up around the outside, and there's stationary sodium on the outside. This is a dynamo which is taking place in 3 pipes. And these pipes, what they do is they limit the magnitude, the size of the eddy that can develop that has turbulence. And it greatly reduces the fluctuation levels and effectively squashes the turbulent resistivity. And so by constraining the flow to be exactly what you want it to be, it turns out to be a great dynamo. And so this violates sort of one principle of dynamos, which is you'd like them to be homogeneous, I think. That's what I mean by a cheat. And I say this in a very respectful way. You're playing with the toy in such a way that you get it to work. In Karlsruhe, they did something else which was really important. They built many small-scale helical flows. The turbulence in this system could only develop on very small scales, so it was a very low level of turbulence. But what they did that was so novel there is they demonstrated that small-scale velocity fluctuations can create large-scale fields. So they imposed scale separation directly through a series of pipes and baffles. So these are the pipes and baffles driven versions of dynamos. Okay? And the Cadarache experiment that I'll talk about, well, so I can say, so this is the sort of thing that was seen. This is the large-scale magnetic field produced by this. Apparently, the turbulence played no role whatsoever in governing the transition. Okay? And I think that's not surprising for this case. It's a little bit more surprising maybe for the von Karman experiment. So let me talk about that. So the most recent experiment, which has very successfully demonstrated dynamos, is kind of a boundary-driven flow. It consists of two counter-rotating disks that have some propeller blades on them, but they're going in opposite directions. And this flow has a centrifugal force that makes a two-vortex flow on average inside the experiment. Okay? And this system, as they increase the flow speed, they observed that a magnetic field started to grow and eventually saturated. So this is a very fine dynamo. You turn up the speed, you turn up the magnetic Reynolds number, and the system becomes a dynamo. Now, there are several things you should know about this experiment. One is, it was only observed that there was a dynamo when the disks are made of iron. So iron is ferromagnetic. In some sense, it acts like an amplifier of the magnetic field, and can be an amplifier by several orders of magnitude even. And so there's a boundary condition effect which is entering in here. The propellers themselves generate some small-scale flow helicity, which may be very important for governing the dynamo. It might, in fact, induce a little alpha effect that has to do with the way that the ferromagnetic material interacts with the dynamo. And these are things which are being fleshed out. Nonetheless, beautiful bifurcation diagrams were measured. Perhaps one of the most troubling things about this early on was the fact that this dynamo doesn't resemble the two-vortex dynamo I showed you at all, which has the magnetic field transverse to the axis of symmetry. It's actually, to the best that they can measure it, an axisymmetric dynamo. And appears to have must have a strong alpha effect to get through Cowling's theorem and behave the way it does. It's an interesting geometry also in that it has a very thickly conducting copper shell on the outside. It has these iron discs in the center. Shear must be playing a role in the middle in producing the toroidal magnetic field, and some alpha effect at the ends is probably necessary to get it to work. Nonetheless, it exhibits a lot of effects that dynamos see in nature. Steady state dynamos are found, periodic dynamos are found, stochastic transitions are found between up and down, basically field reversals are observed. And so this system captures much of that, and the nonlinear dynamics of it is perhaps the most exciting thing to come out of the experiment. Okay?
It seems very symmetric. It seems like it's spending more time in a positive region as compared to negative. At least in
Yes, yes. So one way that they find these different regimes is by spinning the propellers slightly faster in one hemisphere than the other, and by toggling that, they play around.
design.
Mm.
It's not an accident. It's by design. That's how you want it.
That seems to be the case. Yep. Okay. So that brings me to the next step, which is plasma dynamo experiments, and I'll take questions now about everything I've talked about, and then we'll come back and we'll talk about plasma dynamos in the second part.
So you mentioned difficulties of measuring alpha from these kinds of your experiment, because this mean EMF was completely swamped by beta, and it was difficult to pull out alpha.
Not difficult to pull out. It very much is there. The data shows it clearly.
Okay.
No difficult measuring. No difficulty in measuring it.
Okay. So you said it's predominantly in the opposite direction to J, but there is also a component in B direction. And
Not much.
Okay, so could you estimate the alpha?
We tried,
Okay.
but we found very little evidence for it. Now it might be that our flows are just not, they're not rotating flows. They're not dominated by a Coriolis force. The helicity just isn't present on all the scales. So this is a very particular. I think one lesson is that dynamos are not generic. Every dynamo is different.
That's right.
And this setup that we thought was going to be a great dynamo ended up being very turbulent. What I don't understand exactly is, and I'm not sure that the Cadarache people understand this either, is what level of suppression the alpha effect is expected to give in their experiments. They've enhanced their magnetic Reynolds number by adding iron. What we don't know is how much the turbulent resistivity should also be present. And there's an interesting study there. I suspect they see a strong role of turbulence, but they're unable to extract it out in the same way that we've done it. So,
Of course, you did not talk about dynamo number, which comes in mean field calculation. So presumably the dynamo will grow when the dynamo number, which is in different systems, may be different when it crosses a critical value. And when that happens, I would have expected alpha term also to be comparable in strength to the beta term.
You need to drive it in some way. I mean, the alpha effect benefits enormously from scale separation. The beta effect actually works just fine even when you have big fluctuations at the largest scales. So I think that's part of the issue here.
I just going to comment that you could get small scale dynamo to build at large scales by energy going from, so it's basically the triads which make it go.
Yep.
So I'll show you that part a bit later. So what
Oh,
happens
yeah.
is the large scale U couples with small scale B, and then it hops
You need more.
smaller wave numbers. So in fact we don't need helicity either. So non-helical flows, it could without inverse cascade, it's a UB coupling.
Right.
It makes it come down.
Yeah, so one nice thing about these measurements is we don't even have to talk about a cascade. I can measure the mean B, I can measure the mean J, and I measure the turbulent EMF. And we don't even care at which scale the fluctuations are coming with. The most important thing about this, though, in the scale, is that if you have a Kolmogorov-like spectrum, most of the energy in the fluctuations is at the longest scales. Of course, it drops off. Those long scales create a more efficient beta effect than the small scales do. They always will, because the energy is sitting there. So whatever the largest scale is at which the fluctuations exist, that's where you'll see them. So But we just measure what the turbulent EMF is. We average in time, and that's very direct. So, yeah. So I think that's one nice thing about the experiments. I don't have to run my simulations for an infinite period of time to get good correlations because the experiment runs steady state, and I can average as long as I want without, being limited by resolution of my code, for example. No. No, if you look at the predictions for small-scale dynamos in the small Prandtl number limit, these would be very poor small-scale dynamos. The threshold, and Yannick Patti and Alex Chekachian and others worked through, it's very unlikely that this would be a small-scale dynamo. For the large-scale magnetic field, large-scale dynamo, yes.
And the plasma experiments are basically given greater than 1?
Are what? Prandtl number less than 1 to bigger than 1 of order unity, somewhere between 0.1 and 10, depending on, I can adjust it. It's a variable. And that's exciting. Yes. That's how we estimate what the beta effect is. We measure directly the correlation time, and we multiply it by the measured fluctuation energy squared. And that gives us the beta, that's what the beta effect is predicted to be, and that's what we compared then to our measurement. The what? No chance. That's that would be very hard to do. I'd love to be able to measure helicity. I'm not following. Yes.
So, if you said that you didn't find enough alpha in this, alpha was not there.
It was not measured. Not strong. No, we saw very little evidence for an alpha effect.
So, I'm asking, can you measure helicity correlation time instead?
We can't measure even the helicity. Measuring the helicity would require simultaneously measuring velocity at a bunch of different points in order to compute its curl. So the vorticity is a very hard thing to measure unless you have a complicated probe. We didn't get that far. That would be a nice thing to measure.